Hi, and welcome to Chapter 3. We're going to discuss linear regression in this chapter, and we're going to go into much more depth than you've ever spent time on it before. We're also going to talk about, we're actually going to start off with calculator information and walk you through calculator steps. And we'll be using the least squares regression line method, which is probably what you've used before. Since we're doing it with the same calculator that you probably did it with in another class. There are many other methods of linear regression, just so you know. This is just the one that is most commonly taught to high school students and probably the most commonly used one in general. All right, so we are going to start off with calculator stuff. So let me pull that up. And so I want you to follow along here. If you want to put the same data points in your calculator, when I pull those data points up on the screen, please pause the video and type it into your calculator, and feel free to pause as you go to make sure that you're able to reproduce the same outcome with the calculator that I'm producing. Alrighty, so first few things. In the mode button, if you hit mode, if you have this model calculator, you should be able to see where it says statistics or stat diagnostics here, and I want you to arrow down and make sure you turn those on. Okay, now arrow over to on and hit enter, and you got it. Okay, so when you move past it, on stays lit up. Then, by the way, if you have an older model, the way that you find, if you hit mode, you won't see the statistical diagnostics on the screen for the older models. You might have to do second 0 to get the catalog, and then you're going to, you see how there's an A up here? That means you're in alphabetic mode. You're going to hit the letter R, which is in green over here, R, and then you're going to, oh, not R, I'm sorry, it's D. D for diagnostics, and then you're just going to arrow down until you get to the word diagnostics. And literally, this is the only way to get to it in the older models. Diagnostic on, you're going to hit enter, and then you're going to hit enter again until it says done. And that's how you turn the diagnostics on in older models that don't have the expanded mode menu. Okay, so now that you've turned your diagnostic features on, that's how you get your correlation numbers. We're going to go and put in a list. All right, well, I've already entered a list. This list describes in list 1, this is the sodium levels in, I believe it is milligrams, in salads that McDonald's sells. And the second list is grams of fat in the various salads that McDonald's sells. And we're going to see if sodium levels and fat grams are correlated, okay, are associated with one another. Since that's actually associated is a word for categorical variables, we'll look for a correlation between. Now, we're purposefully not looking for causality here, and I'll discuss that a little bit further later, okay? So once we have this data in, we hit second quit. All right, I'm going to clear that out. Clear this out so you can see better what I've hit. And we are going to go to stat calculate, and we're going to go down to linear regression. Now notice there's a 4 and an 8, and I'm going to say that it's much more common for this textbook to use 8 than 4, but because you're an astute math student, you can use whichever one you like. Because here B is the slope, and in the other model A is the slope, and because it's the coefficient of x, you know it's the slope, and you're not going to mess up and read the y-intercept as slope as long as you're paying attention. So please be mindful of which of these numbers is slope by which is the coefficient of x. So it defaults to list 1 as the x-coordinate and list 2 as the y-coordinate, and you do not need to enter anything at all under frequency. Okay, if you'd care to graph this line, you need to put the y equation that you want to enter it in, and I really don't care to enter it in a specific one other than just the first y equation. So there's, let's see, alpha F4 is going to give you this list right here, and I'm just going to put it in y1. That's the quickest way to get to the y variables. I'll say that again. That's going to be alpha F4. And you should have an F4 button on some of the older models that'll get you the same list. That's the short way in. The long way in is to go to vars arrow right to y variables, because var stands for variables, choose a function variable, and then choose number 1. Okay, that's the long way to get in there. Then you're going to arrow down to calculate, hit enter. Now, if your statistical diagnostics are on, you will see both the equation up here, the a and b values, r squared value, and r. If you have not turned your diagnostical features on, is diagnostical a word? I don't know. Diagnostic features, if you haven't turned them on, you won't see the r values, and you'll need to go and turn them on and come back and run the model again. All right. So make sure you realize here that a is the y-intercept, and y-intercept may or may not make any sense, by the way, because we know we're doing the context is where you have to understand whether and decide whether the y-intercept makes sense based on your context. So we're seeing if sodium milligrams can predict fat grams, and there's no such thing as negative sodium in a salad, so you know the y-intercept here doesn't have any real meaning, and that's okay. It doesn't mean the model has no validity. Here we see the slope is 0.02, all right? R squared is 0.7, and R is 0.85 roughly. And when it comes to number of decimal places of accuracy, you really can go by your own judgment. There's not a specified rule. We don't use sig figs, although you could consider that if you'd like. I wouldn't bother with sig figs here. You look at the context of the question, you see what seems to make sense. Do we care about the 5th decimal place of milligrams? That you can answer that question for yourself. I want to say that you should probably never go below 3 decimal places, just if you need a rule, okay? If it makes sense, if it's money, well, then you only need 2 decimal places, okay? There are only a few banking applications where they use more than 2 decimal places. But in the end, when it comes to how much money is in your bank account, they're definitely only using 2 decimal places. So they would use more decimal places when it comes to long-term calculations and projections. And sometimes in various applications where even a tenth of a penny over a long period of time would grow sufficiently. But I'm just going to say when you're doing money, just do 2 decimal places and don't worry about it. Okay, now we did tell it to graph this line. So if we hit the graph button, that's nice. And I already had my graph set to zoom stat, but zoom 9 is zoom stat is the way you ought to go. Okay, now I don't see any of the points from my data. I'd like to see the scatter plot and see the line among the scatter plot. So we've got to go turn the statistical plot on. So hit second y equals, go to whichever plot you care to use, hit enter to turn it on, and then arrow down. The very first plot here is the scatter plot. So hit enter, and it defaults to L1 for X and L2 for Y. If you've done it in another place because you don't want to overwrite your list 1 and list 2, then just make sure when you arrow down to that line, you see how there's L1 and L2 and L3 all the way up to L6 in blue over each of these buttons. That's the second feature. If I needed to list L3 in, I could do it that way. Okay, I'm going to put it back on list 1 though, because that's where my X data is, my explanatory data, right? All right, so now we hit zoom 9. You don't even have to hit graph, you just hit zoom 9. And now you can see the scatter plot and you can see the line. And if you want to turn the line off, but you don't want to erase it, just arrow to the equal sign and see how the cursor's blinking there. Hit enter, and it will unhighlight the equal sign. And so when I go to graph my data, I won't see the line, but it's still in there, so I could just go and put the cursor back on the equal sign and I would see my line again. Okay. So I'll go put it back on, enter, and zoom 9. Alrighty, that's how you do the calculator. If you have any questions in class, please be sure to ask them. Okay, so going back to our PowerPoint. All right, so let's just make sure we get the vocab right. I really hate that they listed the response variable first, because the explanatory variable is the X variable that is the influence that we're trying to see if X influences Y. So the X variable is explaining the Y variable, okay? So the Y, the outcome of the study, is the response variable. And I want you to take special note here. We have not yet gotten to a place where we can say that we are discovering that one characteristic of data influences or causes the outcome and the y variable. We have not gotten that question answered yet, A causing B or causality. We will discuss in Chapter 4 when you're able to do that, but right now we're merely looking for a relationship, okay? So no direct causation yet, just a correlation. And by the way, correlation doesn't necessarily imply that X causes Y. You could have it backwards. So be careful with that so far, all right? So in our scatter plot, there's your memory trick. The explanatory variable goes on the x-axis, x and x. By the way, when you're asked to draw scatter plots, you must label and scale your axes, or the drawing that you draw for your plot will count for nothing, alrighty? All right. So, by way of describing a scatter plot, if you don't give a thorough description that includes the direction, the form, and the strength, and any potential outliers, then you will give a very incomplete definition, or a description rather. The memory trick here is DOFS, D-O-F-S. If you put outlier here between D and F, it's direction, outliers, form, and strength, D-O-F-S, DOFS, if you will. Silly word, just like socks, but it'll help you remember the 4 steps of fully describing a scatter plot. All right, so we're going to see some examples of thorough descriptions, and what we want to mention when we say direction, that's the direction the association takes. So positive association or negative association is essentially slope. Okay, now R value is not slope. Okay, and you'll see that from your calculator data over here. Our R value, if we go to quit, let's run the model again. Calc 8. I'm going to put that back in case I want to see it again. Oh, hit the wrong thing. Alrighty. So stat calc 8, and then arrow down. All right. Alpha F4, there we go, number 1, and calculate. So you can see that our slope is 0.02 and our R value is 0.84977. They are nowhere near each other, so R is not a slope, but if R is positive, the data is positively correlated. If one goes up, the other goes up. If R is negative, the slope is negative, and if one variable goes up, the other goes down. So please do not mistake R for slope. That's a really common error. Okay, so notice the description here. I like that they mention the idea of clusters down here, but let's make sure that you pick up on this. Strength is moderately strong, because you can kind of see a pattern here. All right, the direction is negative, it's going downhill. So as the percentage of people taking the SAT in, I believe this was state data, the average math score goes, okay, so the percent goes up, the average math score goes down. So the more people taking the SAT in a state, the lower the average score. That's been true in Georgia for years. So finally, the form. This data doesn't look like a straight line. I mean, the general pattern is kind of curvy, so they said curved. So you should not get a very good R value, and we'll discuss the appropriate range of R values and what it means in just a moment. But to say this is linear is not a good description. So curved is a good word to describe this particular data. And what you're going to do when it comes to learning to describe these well is pick up on the words that are being used here. Notice they didn't say strong, they said moderately strong. So please qualify with words like moderately, extremely. If it's a weak relationship, say moderately weak or very weak. Don't just say strong or weak, okay? Negative and positive, you don't have to qualify those. Curved or linear, sinusoidal, if you happen to get that, it's pretty rare. Mostly they're at least a little linear. But curved and linear are the two basic categories, and anything more specific than that is probably pretty rare if we're trying to make a straight line out of it. And then I like that they pointed out that this data kind of comes in two chunks, two clusters. So this bottom cluster down here has a very different overall pattern than this top cluster up here. It's when you put them together that we think the data is curved. So there's something different going on over here. These states where not a high percentage of people are taking the SAT are getting awfully high averages. But this is not a straight line relationship. There's something else going on here when we consider them all one graph. So if we were just covering up one part of it and looking at one cluster at a time, we would describe these differently. So point out clusters. Okay, so take a look at this one. This says points per game and wins. So there's some kind of game that's being played. The scores run roughly around 15 to 40, and the more points per game that a team is scoring, the more wins they're having. Well, that makes pretty good sense, okay? But I gotta say, when they're asked to describe the scatter plot and you say positive or negative association, you need to put the context in. Okay, positive association between points per game and wins. So the more points per game a team scores, the more wins they have, or the fewer points they score, the fewer wins they have. Without that, if you just say positive, it's a really weak answer. All right, so form, in this case, we might say linear. So we're trying to think. Direction is positive. We'll talk about outliers in a minute. Form, linear, okay? It generally follows a straight line. The strength, and I like how they describe it here. The points do not vary much from the linear pattern. Clearly, they're not a perfectly straight line, but that is so rare in naturally occurring data. So we want to say fairly strong linear relationship, okay? Then they pointed out there don't seem to be any outliers. This point right here gets pointed up a lot as a potential outlier, but in general, it's not any higher than this one. So I wouldn't say it deviates from the pattern significantly. You know, if it was like up here, that would be weird, all right? So don't think that that makes it an outlier just because it's fairly level with this one over here. Okay. Outliers tend to be gross outliers in questions. They don't want you hemming and hawing for a long time over, oh, is this an outlier or not? They're going to make it pretty obvious. Okay, now R value. Correlation. There's R and there's R squared, and they're different. Okay, right now we're going to talk about correlation only. So this is a number. It's always somewhere between -1 and +1. And if it's positive, it's a positive slope. If R is negative, it's a negative slope, like I said before. But it's not that -1 is a weak relationship and +1 is strong. It's that 0 is weak, and the closer you get to 1 or -1, the stronger the linear relationship. Now you need to understand this number only describes lines. It is possible to have data that is curved that has a high correlation. If you just look at y = x squared on the domain 0 to 10, it has a 0.97 correlation. So it's only talking about the strength of the linear relationship. If the shape of the data is not linear, then correlation means nothing. Okay, so you wouldn't say a strong curved relationship for an R value of 0.97 because it only describes linear relationships. All right. And yeah, again, the whole thing about R being equal to -1 and equal to +1, only if every single dot in the scatter plot perfectly lines up in a straight line are you going to have a perfect R value of 1 or -1. Okay, so it's kind of important that you can eyeball these. I want you to look at these for a moment. You might need to pause it and start to understand. You don't have to be perfect about this, but if you can eyeball a correlation, you can do much better in estimating it. So if they don't give you an R value and they're wanting to know what you think, I want you to practice figuring out what these are. So maybe have this page of the book open to when you're trying to guess some on your own. Okay, so this R value of 0 is just a random cloud of dots. All right, the -0.3, one way to help you judge this is to draw an ellipse that encompasses most of the points, and then you can decide which way it's tilted, and that would give you your positive or negative. And if you take the measure, like literally some people will have this printed on a piece of paper and they will draw that ellipse and they will measure the major axis and the minor axis and look at the ratio of them. And if the ratio of the major axis to the minor axis is a big number, then it's a narrower, flatter ellipse like this might be than, say, this. And there's all kinds of fun little guessing methods like that. But I think after you do this for a short time, you get pretty good at it. But you can start drawing ellipses around these and using that, pardon me, as a way to help you judge correlation. Okay. So this is a formula I've never seen anybody asked about on the AP exam, but this formula is on the AP exam formula sheet. So I encourage you to read through this part of the book, but I would not memorize this. The only thing I would point out about the R formula is if you take a look at it, so here they're kind of deriving the idea, and X bar and Y bar are the mean values of all the X coordinates, the mean values of all the Y coordinates. And of course, these are standard deviation of the X coordinates, standard deviation of the Y coordinates. And you would have, as indicated up here, a pair of these for every point on the scatter plot, and then you would add up all these values. But take a look at the units in this formula. N is just the number of data points. That's not a unit. Whatever the units for X are, or is, units are, xi minus x bar. That's just going to, let's say this is grams. So the unit for the numerator is going to be grams. Let's say the unit here is milligrams, like in our, or that's backwards. For our example before, this was milligrams and this was grams. But standard deviation has the same units as mean and the individual data points. So milligrams over milligrams cancels, and grams over grams cancels. So R is unitless. And you need to understand that when you talk about some things that are coming up. So on this screen, we talk about the fact that R has no unit of measurement. And so we can swap X and Y interchangeably. It does not change what R is. And, just mathematically speaking, if we look at that R formula, if we interchange X and Y, we're just changing the order of this multiplication. And the commutative property of multiplication would tell you that it wouldn't change the R value. So that's very mathematically sound. So there isn't a distinction between which variable is explanatory and which variable is the response variable in the correlation number. Okay, so I think the first caution here is very obvious. All the numbers must be quantitative data. Again, correlation does not talk about curved relationships. It only talks about linear relationships. And so if the relationship is not linear, correlation could mean nothing. Also, outliers really mess with correlation. And so there'll be some homework problems where they put an extreme outlier in the question and then they ask you, how is the slope of the data affected? And I want you to pay particular attention to those questions. All right. So here's a little bit of practice. If you want to pause it, I'll wait a moment and give you my opinion. These may not be perfect, but I just need you to have a little practice, then I'm going to show you a website. So pause it now if you want to guess. And then, okay, my guess here is 0.8, positive 0.8, and my interpretation is the more boats that are registered in Florida in the thousands, the more manatees are killed by those boats. That seems to make sense. Okay, pause again if you don't want to hear it. My estimate here is that this is a positive, I couldn't decide between 0.5 and 0.6, so I'm going to say a positive 0.55. It might be a 6. And my context is that the number of storms predicted has a positive correlation with the number of storms observed, meaning it's a positive relationship. It's not a really strong linear relationship, so I would say that the number of storms predicted isn't always great at predicting the number of storms observed, but it's not terrible either. Okay, if you want to pause this now, go ahead. I'm going to guess that this might have a 0.3 positive relationship. Kind of? I don't know. This one bugs me. But let's see. Healing rate of limb 1, healing rate of limb 2. So it looks like if you have somebody that has 2 limbs injured, the healing rate of 1 is trying to be used as a predictor for the healing rate of limb 2, and it may not be all that good a predictor. All right, finally, go ahead and pause it now if you don't want to hear my answer right away. This data looks somewhat negatively correlated. I'm going to say maybe a negative 0.1. This is it could be even worse than that, closer to zero. But let's see, that last year's percent return, this year's percent return. So return on investment, I'm not sure what the return is, but let's say it is. So last year's percent return on investment is not a good predictor of this year's percent return on investment. All right, so before we go, I want to show you a website, and I want you to maybe pause this and write down rossmanchance.com. That's all you really need to write down, because there are a lot of good applets on this website for our class if you do this entire address. In fact, let me try something real quick. If you just do this part, it'll take you to the main page for these applets. Oh, I should have hit paste and go. Here is the main page. Here's the applet collection, and guess the correlation is the one we're on, but there's all kinds of good practice applets that we'll use in this class. So I'm going to guess the correlation. And here's what we do. You pick the number of data points you want to use. Let's say you want to do a lot, 50 or 100, and you get a new sample. And then you could paste data in here if you want it to figure it out for you, but I think it's easier to do it in a calculator because it has to be arranged. Edit data. Yeah, you could go in here and you could cut and paste and put data in, or edit it to make it look more like you want, if you like that. And then you got to guess what the correlation is. So this really looks really close to zero, frankly. So I'm going to guess 0, and it's going to tell me that it's a negative 0.06. And that's really close to 0. So I did pretty well. Now, if you want to play a game and see how well you do, here you go. And then you could get a new sample and you could try it again. So let's say negative 0.7. I don't know, 0.65. Oh, negative 0.59. Okay, so keeps track of how well I did in different types of graphs, and you could keep going until you're getting really good at it. There's also this game, which is kind of fun, guessthecorrelation.com, and you can play against somebody. So here you go. You try to guess. Oh, that's really scattered. I'm going to say 0.1, and it's 0.09. Okay, so I'm pretty close. And you can score lives and coins, and you can play with a friend. You can put in 2 players. This is kind of a fun game. And until you get really good at it, it's not a bad way to spend a little bit of time becoming good at guessing correlations. Alrighty. Believe that will wrap us up for this lesson. Thank you so much.